All right. We're gonna welcome Luca. So Luca's gonna introduce us to the digital age. I see he's the one with the lapel mic, so he's definitely digital age in the use of microphones and technology. So thanks, Luca. You can take it away. Well, once everyone's in.
Great. Great. Thank you very much, and thank you, Professor, for the nice background. I think I'm still a bit in that losing the plot spot when we look at my talk. There's a bit of mathematics in there, just so everybody knows. But we saw now the historic evolution of statistics, and also how statistics became a formal discipline over the past century. And in my part of the talk, I want to try and highlight how these same ideas are powering today's applications. So the main theme I want to try and highlight is that the modern statistical learning theory relies on classical mathematics, and that computational advancements rather enrich rather than replace the classical mathematics and statistics. And the main overview or the main parts that I want to discuss is a little bit of background on statistical learning and how we can view that as convex optimization in mathematics. And we'll also briefly talk about optimization in extreme value theory, and then go on to a completely different world of deep learning or deep neural networks, and finally end with an example of open set recognition with deep neural networks and extreme value theory. So, as I said, there will be a bit of maths. So essentially, just some background on unconstrained optimization. Suppose we have some function f, which we want to minimize over here, or equivalently, we want to find the x values that minimize some function. Well, in statistical learning theory, often involves minimizing a function or a loss function. So we frequently have problems of this form where we have to find the minimum of a function. And if this function has a nice properties, that it is differentiable and it's a convex function, then essentially we know from calculus that to find this minimum, we need to solve a set of equations where the gradient of this function is equal to 0. Now, frequently, this is quite a hard process to do, and essentially we use numerical approaches to do that. And common approaches include Newton's method, which comes from the 1600s already, and also gradient descent or stochastic gradient descent, which actually comes from Cauchy in the 1800s already. So extremely old methods that still powers today's optimization. Now, going even one step further with optimization, I will look at just briefly a general minimization problem, and just to talk about why this is important in statistical learning. Well, we want to minimize some function subject to a set of constraints, and frequently in supervised learning, we can think of the objective we want to minimize, the f, as some loss function that measures the error we make in predicting with our model. And we can think of the constraints as encoding some domain knowledge about the problem or some regularization terms to essentially regularize our model. And examples of problems that can be phrased in this context are so many, but some of them are ridge regression, lasso regression, support vector machines, to just name a very few of them. And one might ask, how do we actually solve this problem? And to do that, I'll just briefly talk about it. We define something called a Lagrangian, where we replace these hard constraints over here with just some penalties that penalizes our objective we want to minimize for violating these constraints. And from that, we can also see that there's a nice property of the Lagrangian that if x star minimizes our objective function, then we always have this property that the minimum of f of x is bounded from below by the minimum of the Lagrangian if we take that minimum over x. So for any u or v that we plug in here, it will always bound our objective from below. And that's a nice property because now we see we want to make this bound to the minimum as tight as possible. So we essentially want to get d as close to f of x as possible. And that leads to an equivalent formulation for this optimization known as the dual problem, where we essentially want to maximize the dual to make that bound quite tight, subject to some constraints that we want to keep these dual variables positive to make sure when we add these constraints to our objective, they actually penalize the model for violating them and it doesn't decrease the objective for violating the constraints. And a last little bit of background is something known as the KKT conditions. And it's quite interesting that these were first published by Kuhn and Tucker in 1951. And they were then called the KT conditions, but it was later discovered actually that Karush derived the exact same conditions already in his 1939 master's thesis, right? And then it was appropriately renamed to the KKT conditions, which we still use today. And these are a set of conditions which I won't go through in detail. There's 4 of them. But the real nice thing about them is that it can be shown that the KKT conditions are sufficient for optimality. Now that's a great property, so it means if we can find the x variable, or if we can find an x variable and our u and v variables that satisfy these KKT conditions, then those variables provide a solution to the primal problem, they minimize it, and also to the dual problem to maximize the dual. And also under some further assumptions that we can make or some other conditions, we can also show that they are in some cases necessary. So if we found variables that solve the primal and the dual problem, then they have to satisfy the KKT conditions. So why am I talking about all of this? Well, in statistical learning, a lot of problems can be phrased as convex optimization problems. And to give one example, or I'll give 2 examples, where the first one is the lasso regression. And we all have seen this problem before. We want to apply linear regression subject to the constraints that the L1 norm of our regression coefficient is less than or equal to some t. Now, this is a very hard problem to solve, as it is over there. But using the KKT conditions, actually, we can show an equivalent form of this problem in the classic loss plus penalty formulation, where we essentially regularize our regression coefficients with our L1 norm over here. And it's much easier to vary lambda and to solve this problem than to vary t and to solve the constrained optimization problem. Now, as we said right at the beginning, how we would solve this is take gradients of this objective and set them equal to 0. But in this case, there's a slight technical detail that the L1 norm is not differentiable at 0. So we actually extend gradients to something called subgradients. And then by setting them equal to 0, we get a nice set of normal equations or optimality conditions, which are given over here. But as we see, we can't really solve for beta from these equations. So we need something more to actually estimate the coefficients in this model. So we can think of it as these optimality conditions are useful to check if a solution is optimal, but it doesn't really provide us with a way to actually estimate the coefficients in the lasso. So for that, we need a numerical procedure, and that's where our digital age comes in, where we can numerically approximate these coefficients by applying some algorithm based on this theory. So to do that, we can use a method known as coordinate descent, and this is a very popular method for the lasso and also for other problems, which we'll see. So the idea behind coordinate descent is, why don't we single out a single coefficient, a beta j, and its corresponding feature, the xj, and we denote the rest of the loss over there as the residuals, where we predict with a model that excluded that beta j. So now we actually have a univariate problem, which is much easier to solve. And by going through the exact same steps, getting our optimality conditions, we actually have an analytical solution for that single beta j, which is just soft thresholding the least square solution, where we regress the xj on the residuals. So we see here we have a very nice analytical solution for a single beta j, but the problem is that the rest of the betas are still contained in the residuals. So we can't just go through this once and change beta, but we have to continuously go through all the different coefficients until we have reached some convergence. So the general coordinate descent for the lasso is to iteratively loop through all the features, and at the jth iteration, we use this analytical expression to update beta. And now that we've updated beta, we can use it to update our residuals again, so we can update the next beta. And therefore, we update the residuals. And this process is continued until we have converged, actually. So just to briefly talk about coordinate descent further, it's a very frequently used or very popular algorithm that's deployed in packages like the glmnet package in R, which is a very well-known package, also in the lasso class of scikit-learn in Python. And we can really, it's a really efficient algorithm which can be deployed at scale to solve this lasso problem. And here you can just see in the documentation, they use coordinate descent, and also over there to just make sure I'm not lying to everyone here tonight. And then also another nice feature of the coordinate descent algorithm is that because it solves one variable at a time, it naturally extends to the case where we have a lot more features, where P is much larger than our sample size N, because we're just solving one feature at a time. And as an example, there's this Kaggle notebook, which I'll give the reference at the end, where they try to predict 5 types of leukemia using only 64 observations, but more than 22,000 variables, right? So an extremely difficult problem. And the approach this user followed was to first use the lasso with coordinate descent to select 21 of the approximately 22,000 features, and thereafter, using only these 21 features and the 64 observations, fit a neural network to predict the 5 types of leukemia. And we can see here the significant increase from the pink bars over here in our test accuracy on new data by actually using this lasso as a method to select features before fitting a neural network to this data. More than a double increase in the balanced accuracy. Then also just to mention other methods like the support vector machines also use coordinate descent or type of coordinate descent for estimation. And I will just very briefly highlight some things here. I think the one nice thing of support vector machines is also that the KKT conditions from mathematics, again, give us a nice intuitive interpretation of the problem. And then we can maybe just briefly talk about how we actually estimate this model. So the idea of support vector machines, for those who haven't worked with it, is essentially to estimate a hyperplane that separates 2 classes of data which we want to classify in, and we estimate that hyperplane to have maximum margin between the data points from the different classes. Now, there might be some points that violate this margin or that fall inside the margin or are misclassified by the model, and to deal with those points, we include slack variables in the problem, essentially. But we can phrase the entire support vector machine classifier as a convex optimization problem again in this constrained optimization world. And without giving the details, it can be shown that the dual is just a function of the dual variables that are linked to the margin violation constraints. So essentially, these positive variables that govern the influence of these violations into the margin or the misclassifications. And also, just briefly, that the dual is subject to 2 sets of constraints. Box constraints, meaning that each alpha I must be between 0 and C, as well as this equality constraint over here. And C is just a hyperparameter that controls how much we penalize these misclassifications or margin violations. Now, what do the KKT conditions tell us about this problem? Well, firstly, it's only the alpha I values, or only the points that lie on the margin, within the margin, or are misclassified by the model will have positive alpha i's, so positive dual variables. All the other ones are 0. Also, from the stationarity condition, we see that the slope parameter of this hyperplane, denoted by W, is just also a function of these alpha i's. Now, because only some of them are non-zero, we can say it's a sparse solution in the data. So essentially, that's useful for prediction, firstly, because we don't have to compute it over all the data points. We just have to use these non-zero support vectors. But it's also very useful for optimization, because we only have to consider those that lie on the margin or within the margin. And lastly, we also see from the dual and from the solution of this vector W that evaluating the dual or the hyperplane at a point x only depends on inner products between that point x and the data xi. And by using the lovely mathematical theory from reproducing kernel Hilbert spaces, it allows us to actually kernelize this method, where we replace this inner product in the dual and in the hyperplane with essentially a kernel which implicitly maps the data to a higher dimension, where it computes the inner product, and that corresponds to fitting a nonlinear decision boundary in the original data space. So really we see that the convex optimization theory really helps us to understand this method a lot better, and it also helps us to estimate these alpha i's. Because something we skip over a lot in statistical learning is to how do we actually estimate these alpha i's. And to give a very short summary of that, there are various methods to do that, but all of them are essentially coordinate descent again. So if we do not have kernels and we work with linear support vector machines in very large-scale problems, then generally we apply coordinate descent on the dual. And you can have a look at the liblinear C++ implementation, where they talk about applying coordinate descent. But when we have kernels, there's actually another algorithm called Platt's sequential minimal optimization, which is also applied in the dual space, and that works for kernels. And if you look at the libsvm C++ implementations, they refer to this algorithm over here. So I call Platt's SMO a type of double coordinate descent. So it's still coordinate descent, but if you remember, the dual had an equality constraint in it. So we can't update one coordinate because we have to make sure we satisfy that equality constraint. So to get around that, this algorithm essentially chooses two alpha values. We first find one that violates the KKT conditions, and then we choose any other alpha j. And then using the constraint, the equality constraint from the dual, we can actually eliminate the one alpha I, and it leads to a one-dimensional quadratic problem in the alpha j. And now using this 1D problem, we can easily find an analytical solution for this quadratic problem. And then we remember we still had the box constraint. So we clip it somehow to ensure that alpha j remains between 0 and c. And now finally, again, using this equality constraint, we can essentially solve for alpha I after we've estimated alpha j. And we just continue to repeat all of these steps until all the alpha i's satisfy our KKT conditions, and then we've arrived at a solution. So I hope you see that optimization plays a key role in statistical learning through these examples. So maybe just to touch a bit on optimization extreme value theory. So besides that, we see that mathematics and these established mathematics essentially provide us with guidance to develop the algorithms. It's really the modern computing that enables us to deploy these ideas at scale. And besides guiding us to develop algorithms, optimization is also crucial because it provides proofs of existence, uniqueness, or optimality of a solution, as well as ways to investigate the rate of convergence towards an optimal solution. But optimization is also fundamental in extreme value theory, because whenever we want to fit an extreme value distribution, we have to estimate some parameters of that distribution, and generally that involves maximizing a likelihood function. But unfortunately, there's no analytical solutions that we can write out to maximize the likelihood, so we require, again, numerical optimization. And to complicate matters even further, it's not necessarily a convex optimization problem. So in that case, we only have slower convergence guarantees, and we can only guarantee convergence to a local optimum, not to a global optimum. Now, in terms of maximum likelihood estimation, there are a variety of optimizers that are frequently used. The most common ones are Newton's method or quasi-Newton methods, where we approximate the inverse of the Hessian, or Fisher's scoring and Nelder-Mead. But I maybe just want to highlight that in extreme value research, there's a very rich in asymptotic theory to investigate the asymptotics. However, the numerical optimization aspects in EVT are not so often considered. And when we apply EVT at scale with big data, it's important to also investigate questions like how are these likelihoods solved at scale? What convergence checks do we have when we apply this numerical optimization? And are there any boundary or pathological cases in the parameter space that we need to be aware of? So perhaps there is some opportunity for algorithmic innovation. And I'd like to highlight a particular paper from Dr. Sven Buitendach, who's here today as well, and others, who considered a second-order approximation for the limiting result in extreme value theory. And then they phrased the estimation of gamma as a regression problem with an L2 or a ridge penalty on that model. So this is a very nice blend of statistical learning theory and extreme value theory, and it perhaps shows potential avenues that can be further explored for some algorithmic innovation in extreme value theory. So now I get to my second part, which is a complete different story. And I want to talk a bit about deep learning because it's so popular today as well. So I think it's important to highlight how this fits into our digital age. So I'll first give some background on deep learning and then try and highlight why statistics is still important in a field that feels like it's purely just practical and computer-driven. So already in 1943, McCullough and Pitts proposed the artificial neuron, and it was the first formal model linking neuronal activity to logic operations. So perhaps this inspired that cognition could be analyzed as computation and network of simple elements, which is debatable still. And then a very famous model, the perceptron, was defined about 15 years later, which is a linear model. And Rosenblatt actually built a theoretical model as well as a mechanical implementation of this model, where it adjusted the weights in the model based on the errors it makes, or the sample errors. And this is one of the first demonstrations of learning from the data, as what we know today. And it fueled an initial surge of interest in neural network research. But unfortunately, about 10 years later, Minsky and Papert mathematically analyzed the perceptron, and they found that it has quite a few limitations. For example, it can only separate, or it can only be applied to linear separable data, meaning that it couldn't solve nonlinear problems. And many interpreted this as a dead end for neural networks, and it led to an AI winter where researchers and also funders lost interest in artificial neural network research. But around the same time in 1970, Lenneinma, a Finnish mathematician, actually developed reverse mode automatic differentiation also in his master's thesis, which is very impressive. And although not in the context of neural networks, he essentially showed how you can compute the analytical gradient of arbitrary functions by first representing it as a computation graph and then moving in the reversed order through that graph, so reverse mode automatic differentiation. But it was only in 1986 that Rumelhart, Hinton, and Williams really popularized backpropagation for training neural networks. So they actually derived the weight update rule that we use in backpropagation for multi-layer perceptrons. And they also showed how we can propagate or accumulate the error layer by layer by moving backwards through this computation graph. They also demonstrated that when we train a multi-layer perceptron, we can discover useful representations on the internal layers. Then from the 90s until now, there's a bit of a deep learning boom, and I think it can be attributed to the developments of new architectures, the availability of big data, such as the ImageNet dataset, which consists of over 1,000 different categories of images that we want to classify them into, and also the significant advances in computing, so being able to compute on a GPU. So these factors really accelerated deep learning to heights unimaginable during that AI winter. And today, these brilliant theoretical and technological breakthroughs are still powering the modern large language models, or your chatbots that we all like to use so much. So really brilliant theory and technological breakthroughs led us to where we are now. So just to mention something on backpropagation, I won't go into any detail really, but when we train a neural network, we need to train it with stochastic gradient descent. So as stated in the word, we need to find the gradients of our loss function with respect to all the parameters in the model. And this is quite hard to do without this nice reverse mode automatic differentiation, where we can essentially break up this model into simpler operations, which we call layers. And then by having the output of the model, we can move in the reverse order or the backward mode of that computation graph and recursively apply the chain rule to compute the gradient of the loss with respect to any of the inputs or any of the weights in the models. So all I want to say here is that backpropagation is recursive application of the chain rule from calculus, and also that network architectures mostly consist out of matrix multiplication. So predicting with the model is a bunch of matrix multiplication, and actually computing the gradient is also mostly matrix multiplication. So there are several very efficient implementations of matrix multiplication. For example, QBLAS and cuDNN are the CUDA libraries from NVIDIA to really efficiently implement matrix multiplication. And these tools are what make it possible to essentially train these neural networks at massive scales. And deep learning libraries such as TensorFlow or PyTorch, they use these CUDA libraries in the back end to accelerate computations on a GPU, so a graphics processing unit. And essentially, it allows one to apply this matrix multiplication and training functions massively in parallel to really scale them to extremely big models. And also, maybe lastly here, is that software exploits the architectures of these neural networks, which generally consist of repeated operations, just taking different inputs and weights, to simplify the whole training process and backpropagation. So by just defining the forward path through the model, so the prediction of the model, the software can automatically compute the gradient or the backward path for one. And I just want to note again that most architectures, including convolutional neural networks, recurrent networks, and even the transformer architectures used in large language models, generally boils down to general matrix multiply operations. So really, this matrix multiplication operations is what enable us to do this at scale. There are some proposals for even more efficient implementations, but in general, it boils down to this matrix multiplication. So now, one might ask, as these models get bigger and more complex, what is the role of statistics really in deep learning? Because it feels like just a computer program and a model that we just fit on all the data. And just to highlight how complex and large these models have become, I have two examples here. So CovNext X large is a convolutional neural network, and it's 350 million parameters. But this model achieves about 87% accuracy on the ImageNet dataset, which consists of 1,000 classes into which one has to classify the data. And now if we go to large language models, it really goes to another scale. So if we think of DeepSeek R1, for example, that model has over 600 billion parameters. So insanely big. But these models are constantly achieving better performance across a variety of benchmarks. And these benchmarks are things like question answering, coding, mathematical reasoning, visual reasoning, things like that. And it keeps just getting better. But with the wide adoption and also the range of applications where we apply these neural networks, there are some new complex challenges that actually arise. And statistics remains fundamental in addressing some of these challenges, and I will highlight a few of them, also trying to give some indication of where statistics plays a key role in addressing these problems. So perhaps a bit more foundational is regularization. So because these models are so big, they're prone to overfit the training data without proper regularization. And regularization techniques are really rooted in classical statistics, and I'll just give two examples of this over here. The first one is dropout, which is frequently used in neural networks. And using dropout during training can actually be viewed as training an enormous ensemble of neural networks, where the neural networks share weights between the ensemble. And by viewing dropout as a type of bagged ensemble, it actually helps us to understand better why the model generalizes well. So how does it actually regularize the model? Or what does it do when we apply dropout? And also early stopping is another tool used to regularize neural networks. And this can be viewed as a practical data-driven model selection approach or controlling model complexity. So there's also, if we think about regularization like ridge regression or something like that, there's a hyperparameter, and we generally have to select that hyperparameter using a grid search. Now, in early stopping, there's also an implicit hyperparameter, the number of steps through the data that we take, but this data-driven approach helps us to automatically select that parameter during training. So we see statistical frameworks help us to better understand the training dynamics of neural networks and also help us understand why how and when they will generalize effectively. Now, another key role statistics plays is interpretability. So we know that in all statistical applications, interpretability is fundamental. But as these models, especially these deep learning models, become extremely complex, it's much harder to actually interpret these models. So traditional tools such as LIME or the shapely values are somewhat limited, especially if we think about large language models where there's varying length of inputs and all of that. And these methods over here try to describe how the input to the model is responsible for the prediction, the output. Nevertheless, there have been some developments in this field, and something like token shop is a very recent method where they modify the shapely values to apply them to variable length inputs, and this way they can measure the importance of each token in a prompt to generate a specific response. And the authors showed that token shop can effectively detect when random words are injected into a prompt, because these random words are less important in generating the response from the model. But it's still very limited in good interpretability, so this led to a whole new field which is called mechanistic interpretability. And in this sense, rather than understanding how the inputs to the model affect the predictions, one is interested in understanding the internal workings of the large language model. So do the internal activations or the outputs on the hidden layers learn certain concepts or certain things about really abstract concepts that it can represent? And I want to just show two such methods. And again, here to highlight the use of statistics here, I want to emphasize the first method is based on classical ideas from linear models, and we'll see it's all linear classifiers that we use. And the second one is based on the idea of enforcing sparsity in the model to, again, have a simple model to understand the internal workings of these large language models better. So the first one, called linear probing, which is a supervised problem. And what we do there is you take a bunch of text And this is supervised, so meaning each bit of input has an associated concept or a label linked to it. So this could be like emotion, or it could be the truth, or if it's truth or false, or it could encode some linguistic characteristics like parts of speech that we want to tag. And then we pass this text through the large language model and we extract some internal activations. And we use this internal activations as our training data together with the label. And then we fit a linear model on those internal activations to try and predict certain interpretable concepts which we've labeled in the data. And if we achieve good accuracy here, then it indicates that the large language model encodes certain linguistic or conceptual information, because in this activation space, these concepts are linearly separable. But this is also a little bit limiting because we have to actually know what the concepts are that it's learning. So a more recent advancement in this interpretability field is sparse autoencoders, which is really a hot topic at the moment in large language model interpretability. And the idea here is to use something called a sparse autoencoder. So it does the opposite thing of the compression of a normal autoencoder, where it has one hidden layer which is much wider than the input. So we have way more features in the hidden layer than we have input features, but we impose a sparsity constraint on that hidden layer, with traditionally using an L1 norm again. Now the idea here is to train an unsupervised model that can reconstruct its input, and by doing so we learn this sparse encoded features in the autoencoder. And the sparsity means that most of the nodes, or most of the values on that hidden layer, will just be 0, and only a few of them will be non-zero because of this penalty. And then we can see, do certain text always correspond to the same nodes being activated in that sparse autoencoder? So do they encode certain conceptual information from the data? And just to show you briefly how this works, is there's a nice demo called GemmaScope, and I give the link at the end. And here you can play with sparse autoencoders that they've actually trained on their large language models. And for example, there's this piece of text here, and we can click on the word volcanic. And then what it does is it shows what are the sparse features that they've already labeled that are mostly associated with the word volcanic. So what sparse features does the word volcanic activate? And if we look at it, we see the features it activates are things like references to volcanic activity and eruptions, or references to natural disasters and the response to them. So we see the word volcanic is associated with these conceptual meanings. Now, if we click on this over here, then it shows us which words are mostly associated with this sparse feature. And we see it's things like volcano, eruption, volcanic lava, which makes a lot of sense. And it also shows the words that are least associated with this feature, and things like dragonfly and leaf and thing. It has nothing to do with volcanoes, right? And just to really try and take it home, the message that they do learn these concepts with the sparse autoencoders, Gemma microscope or GemmaScope allows one to steer the model with these features. So what you can do is essentially find this feature from the sparse autoencoder, and here I use the feature that refuses to answer you, right? So you can extract this, and they find this. If this thing is activated in the large language model, then it will always generate this type of response. It will always not respond, irrespective of the text. So before I add any strength to it, I just ask both the models, complete this with one word, humans live on planet, and it answers Earth, right? So it can actually do it. Now we're going to increase the strength of this feature we found with the sparse autoencoder. And what that does is it means irrespective of what I prompt it, it will always activate that hidden representation in the large language model, and that will steer or guide the response some way. So when we add the strength and I ask it the exact same question, then it generates the following response to me. I cannot complete this request. My purpose is to provide safe and ethical information. This statement could be interpreted as promoting illegal or harmful activity, and I'm programmed to follow these ethical limitations. It is important to understand that any attempt to fulfill this request would be extremely harmful, illegal, and unethical, right? So we see we can really steer these models so that these features actually do represent certain concepts that the models use to formulate their prediction, right, or when they generate a response. And just a few more examples that I want to quickly give you is another big role of statistics is in these generalization puzzles. So as these models become so complex, and we have so many parameters, and they're so difficult to interpret, and we apply them to ever bigger problems, there's some new phenomena which at a glance really seem to contradict traditional views. So two of them is, we'll start with the first one, which is double descent curves. So those who've done statistical learning know that we always talk about the bias-variance trade-off, that as model complexity increases, we initially see a decrease in the test error, and at some point we start to overfit, and then our test error increases again, the classic U-shape. But now with the double descent, it was observed empirically that if we just keep making the model complexity bigger and bigger and bigger past the overfitting limit, then suddenly the test error starts to decrease again, which really contradicts the traditional views of rigorization and complexity. So a very strange empirical observation. Now, those interested in this can refer to Trevor Hastie and others' paper in 2022, where they really provided a theoretical analysis of this phenomenon from a statistical learning theory point of view. Then another strange phenomenon that we observe is something called benign overfitting. So under what conditions is overfitting the training data benign? So meaning we can again fit such a complex model that it interpolates the training data at a zero training error, but somehow it still generalizes well. And Bartlett and others showed in 2020, they provided the conditions under which a minimum norm interpolating linear model exhibits benign overfitting. And recent work, and I give some references here that's also in the end, considered benign overfitting in neural networks, and this is to theoretically explain how can these over-parameterized models with so many parameters still end up generalizing effectively, and they provide necessary conditions on the signal-to-noise ratio in the data. And I think that's interesting because that gives some insight to why things like models fit to image data, video data, audio data, text data seem to be so overly complex, but they generalize well because there's a lot of signal in that data compared to noise. And that's why there's this whole threshold on the signal-to-noise ratio. So this example is taken from Introduction to Statistical Learning with R, and we can see here the double descent curve in our test error as we move past the number of training observations. This is also just to show the different fits that we get with a model that has more parameters than data points, right? And here we see the double descent curve observed when training a neural network from this article. And then also just to show again the benign overfitting phenomenon on the MNIST digits data of a neural network, where we see it is dependent on the scaled signal-to-noise ratio. So as the signal increases relative to the noise, we're more likely to have benign overfitting. So meaning we can overfit the training data, but it still generalizes effectively. And I really just want to emphasize that none of these researchers advocate that overly complex models generalize better and that we should just use overly complex models. They rather study the exact statistical conditions under which we might observe these phenomena, right? So it's really more of when can this happen rather than we should use more complex models because we observe this. And then a last one I want to briefly highlight is uncertainty quantification. So models generally just give a point estimate, but how do we know that we can trust this prediction? And uncertainty quantification allows us to estimate the predictive uncertainty in a model, and this is really based on a lot of statistical frameworks. So for example, Bayesian neural networks, where we actually model all the parameters or the distribution of the parameters using Bayesian inference. And this provides us with a probabilistic model with natural uncertainty quantification, but it is extremely computationally expensive. So Monte Carlo dropout has been shown to be a cheap approximation to this Bayesian inference. So we can actually perform dropout during prediction to have a cheap approximation of a Bayesian neural network. And that gives us a scalable method for uncertainty quantification. And other related problems to uncertainty quantification has been tackled with extreme value theory. And there again, we see the influence of statistics in deep learning. So this is really my last slide on neural networks. So just as an example, something I did, can you spot a difference between these two images over here? And the answer is probably no. You shouldn't really spot a difference. But if we take a standard convolutional neural network, it predicts for image A a lionfish, which is correct, with 99.99% probability. It's very certain. But for some reason, it predicts a robin, a bird, with 99.98% probability for B. So why does it do that? Which is very strange. So now using Monte Carlo dropout, it allows us to estimate the uncertainty through the entropy. And it also predicts lionfish with about 99% probability for A, and an entropy or uncertainty measure of 0.03. But for B, it also predicts robin, still with a very large probability, but we see a 10-fold increase in the entropy or the uncertainty, showing that there's something that's making the model uncertain about its prediction for image B. And then our model, which uses extreme value theory, explicitly predicts the probability that the input is not from any of the known classes. And in our case, it predicts lionfish with 99% probability and 0% uncertainty for A, but it predicts about a 68% probability that B is from none of the known classes, which is great. And what is the difference between these images? Well, I tampered with image B using a targeted adversarial attack where you essentially change the pixels in the image to make the model predict the wrong class. And it's great to see that these methods of uncertainty quantification essentially detects that there's something wrong with this image and it's unsure about its prediction. So as a final one, to finish off, I'd just like to give a short example as well of where we use extreme value theory to address the problem of open set recognition, which we've done in our own research. So just to define open set recognition, generally in multi-class classification, we assume a fixed number of known classes. Now, what if the model will encounter a sample from a class that was not available during training? Now, because traditional classifiers assume a fixed number of known classes, it will automatically predict such a new class to one of the known categories. So open set recognition extends the idea of multi-class classification, where we assume that unknowns are encountered during prediction, and the model must learn only from the data of the known classes to classify them accurately, but it must also learn to detect samples from new classes that were not available during the training of the model. Now, we can assume that unknowns are sufficiently dissimilar to the known classes, and because there have to be some way to detect these unknowns. So if we have a dissimilarity score that measures the dissimilarity between a sample and the known classes, then we expect the unknown classes to have dissimilarity score that's much higher than that of the known classes. So essentially, the unknowns are located in the upper tail of the dissimilarity score, possibly requiring extrapolation beyond the dissimilarity scores of the known classes. And extreme value theory provides us with a statistically sound framework to model the tail distribution of a dissimilarity score, and then we can essentially extrapolate with this estimated distribution beyond the known class training data. And this provides a probabilistic model for open set recognition, and there are various methods that have been proposed, and I'll give some references at the end. And today I'll really in 2 slides showcase our latest development, our model under development DOR EVT, so that is deep open set recognition based on extreme value theory. And this is an end-to-end neural network where we incorporate the extreme value theory from statistics directly into the neural network to perform open set recognition. So the idea is to extend a convolutional neural network with a bunch of new layers, and these layers first estimate a dissimilarity score to essentially say that if samples are from the same class, they have low dissimilarity and they are close together, and if samples are from different classes, they are far apart, high dissimilarity. And we use the contrastive central loss to estimate that embedding. Then we also add a new layer to actually estimate the cumulative distribution function of the dissimilarity score with the generalized Pareto distribution from extreme value theory. And we use this as an estimate of the probability that the samples from an unknown class. Now, the GPD has a set of parameters, so we estimate them during training of the convolutional neural network by minimizing the negative log likelihood. And finally, we use the probability that the samples from an unknown class to adjust these initial probabilities for the known classes to account for the chance that there's a sample from a new unknown class. And the entire model is trained end-to-end using stochastic gradient descent and backpropagation. And just want to highlight that this is the first method that includes the EVT modeling directly into the neural network training for open set recognition. And the first question might be, can we still use stochastic gradient descent to estimate these GPD parameters? Well, we're still busy investigating, but so far it looks good. So here we did a short simulation and compared it to standard software implementations, where we can see it does quite well. And by explicitly outputting this probability of an unknown class, by using extreme value theory, it doesn't scale the known class probabilities after training, which previous methods do. So this leads to more reliable validation of the model during training, and it also has good generalization performance if we compare how it discriminates between unknown and known compared to other methods like evidential deep learning. And also, because we are explicitly predicting the probability of an unknown class with EVT, it allows us to visualize which features in the image are responsible for predicting unknown. And just to give a short example of this, where we can predict the regions in the image responsible for classifying it as known or unknown, we first see a sample from a known class, and with this model, we can apply a tool only because we're estimating the probability of an unknown class with the GPD, and it shows that clearly the bird species is the thing that's making it predict a certain class. There's nothing in this image that's making the model think it's an image from an unknown class. Now, if we look at an unknown species of birds and we put it through the model, then we see it actually doesn't identify anything other than a little bit of background in this image as looking similar to that of the known classes, but it's the actual new species of birds that's responsible for making the model predict an unknown class. And that's a really nice result because it shows it's not distributional shifts, but actually the categories that's changing that's responsible for changing the model's prediction to an unknown class. So that is my story. And to just maybe conclude very briefly, we saw now from Fisher blend of biology and mathematics and Dehaan's combination of mathematical analysis and EVT, and now also deep learning's fusion of linear algebra, optimization, and computer science, that these breakthroughs and steps forwards often comes from collaboration between different disciplines. So we should be open to the interdisciplinary collaboration always. And modern software makes analyses seem very easy to us, but yet all these tools are built on established results from mathematics, statistics, and computer science. So in order to be able to extend them, understand them, or to critique these methods demands a solid theoretical foundation. And interpretable and ethical statistics is really important today with the adoption of these complex and black box models. And statistics offers us a principled framework to quantify uncertainty, assessing fairness, and to actually interpret these black box models. And continuous engagement here with both foundational theory and modern computational practice will best equip our scholars to shape the next advances in statistics. So thank you very much, everyone. And there's a set of references.
Lastly, I just want to thank Luca very much and Prof. Tibet as well. I think it was a tour de force. It's not for the faint of heart. Got a strong stomach today too. Those pictures I got lost in a little bit, but that's just. I'm glad there's people that understand. I'm glad there's people that are taking care of the interpretability of what all these gurus are doing with big data. So I'm grateful. Once again, thank you, Luca and Prof. Tibet. We've got a small gift for each of you. I just want to say thank you. Luca, if you wouldn't mind coming here, stepping up behind the curtain. Thank you so much. And then Prof. Tibet as well. We really appreciate it. We really appreciate Prof. Tibet for helping us tonight. Again, a tour de force, and we thank you. There's usually a question and answer after these sessions, but we're going to do the question and answer at the back if you want to. So please join us afterwards for some eats, some drinks,